now that you've seen Newman projections and how they can be used to show different conformations of molecules, let's use that to explain the observation that when when ethane rotates around its carbon-carbon single bond, it spends most of its time in the staggered conformation and less of its time in the eclipsed conformation. So recall that there's kind of two extremes of conformations for ethane. We have the staggered conformer, which is on the left, and the eclipsed conformer on the right. The staggered conformer, we say, it's more stable and it's lower in energy. It's not as likely to change as the conformer on the right, which is less stable, it's higher in energy, and it's more likely to change. And so what makes those different is probably two things. One, in the staggered conformer, the electron clouds for the carbon-hydrogen bonds are as far apart as possible. And there's also probably orbital overlap between the bonding orbital, between the CH bond on the right side, and the anti-bonding orbital, which you can't see, which is on the left side. We'll talk more about that overlap and why that is stabilizing next semester. For now, just note that those two things are stabilizing for the staggered conformer, and they're both not there for the eclipsed conformer. So there's a difference in energy between these two, and we can graph that. And this is one of these things that we do in conformational analysis, is that we graph the energy as we turn or as there's rotation about the single bond. So what's being done here is that the bond, that carbon-hydrogen in the bond in the back is being fixed. So it's going to stay in the same place. And then the hydrogen that's in the front, it starts here anti to it's in the staggered conformer, this hydrogen, it's just kind of randomly selected, it's in the front, and it's anti to the hydrogen on the bottom. And so then we rotate 60 degrees and we wind up with an eclipse conformer. Notice that hydrogen in the back is still there. The hydrogen in the front is now at 60 degrees clockwise. And then we keep turning 60 degrees. We get that staggered conformer again, then eclipse conformer, and we keep turning until we've rotated entirely around that single bond and we wind up back in that anti-conformation. So if we think about the relative energy, remember, as we said, the staggered conformers are lower in energy, they're more stable, they're more likely to change, or pardon me, less likely to change. And then we have higher energy, which is the eclipsed, and those are less stable, and sort of by definition, less stable things are more likely to change. It's kind of like standing up on top of a table. You're more likely to fall than if you were on the ground, which is down here. Or similarly, if you took an electron and pulled it away from the nucleus a little bit, it would want to go back to the ground state. So if we think about kind of how the energy changes as we do this rotation, it ends up being this nice kind of sine curve where as the hydrogens get closer to each other, the energy goes up until you get this maximum of the eclipsed. And then as they rotate away from each other, the energy goes back down to a more stable conformation. And we get to something where we get to that staggered conformation. And it just kind of goes back and forth, back and forth. So notice that the height between the lowest and highest energy conformation is 12 kilojoules per mole. And so that can be measured by looking at the relative amounts of these different conformers in solution at any one time. And so if we think of each of these carbon-hydrogen bonds as contributing a third to that 12 kilojoules per mole, we come up with energy, we call it energy of torsional strain. In other words, it's this eclipsing interaction here. And so each of those hydrogen-hydrogen eclipsing interactions gives us 4 kilojoules per mole of this torsional strain. And so because these, just to kind of answer our question here, because the eclipsing or the eclipse conformation is higher in energy than the staggered conformation, that's why we see, to go back. Where did it go? There it is. That's why we see when we get in eclipsing interaction, this molecule is more likely to change. It just doesn't want to be in that eclipsed interaction. It doesn't stay there very long. It's high energy, but the staggered conformation is lower in energy. Okay. So let's look at a more complicated example. Look at the example of butane. And butane, remember, also has that gauche interaction as well as the anti, where the methyl groups are opposite from one another. And so we're going to do the same thing here. Start with the anti-conformation. This time the methyl groups will be anti, and then go hold the back fixed and then rotate the front methyl group around, or rotate the front carbon around until we get complete rotation about the single bond. And we are looking at this, we're kind of sighting down the C2, C3 axis. We're not looking at carbon 3 or carbon to carbon 4 single bond or carbon 1 to carbon 2. We're looking at that middle bond. So think for a moment what you would expect to be the lowest energy conformation and the highest energy conformation. So the highest energy is where those methyl groups are eclipsing one another, and you can see it's 19 kilojoules per mole. Lowest energy is that anti-conformation. But we do get these different, we don't just have staggered and eclipse. We have the staggered anti, then we have some eclipsed interactions where it's the methyl and hydrogen that are eclipsing each other. Those are the same on either side. And as we rotate around, again, we're rotating, keeping that back fixed and rotating the front methyl group clockwise, pardon me. We get those gauche interactions that are a little bit higher in energy than the anti, but not nearly as high in energy as the eclipse conformations. So there's 2 of those, and then we wind up back at the anti-conformation. So again, figuring out sort of what the contribution to the total energy is of each of these types of interactions. So, I mean, we've got a bunch of different types of interactions here. We have methyl eclipsing, we have hydrogen eclipsing, we have hydrogen and methyl eclipsing. We have these gauche interactions down here that can all contribute to the energy. And so what you would do if you were trying to figure out why this is 16 kilojoules per mole is you'd say, well, look, there's one hydrogen-hydrogen eclipsing interaction, that's 4, and then there's 2 of these hydrogen methyl, and each of those is 12. Or each of those is 6, so that's 12 in all because there's 2, one here and one here. So 6 plus 4 is the 16 down here. Okay, so that's how we get these numbers. This one's higher because we have the methyls eclipsing, so that's 11. And then we have 2 hydrogens, each of those is 4. So 11 plus 4 is 15, plus another 4 is 19, so that's 19 kilojoules per mole. One of the things you might notice, or what this asks up here, is what conformation does butane spend the most time in? And remember that the more stable it is, the more likely it is to not change. And so these anti-conformations is where butane spends the most time. And maybe this is surprising to you, maybe not, but if we think about how we draw this with a bond line structure, this is actually a staggered conformation. We go down one bond, and then we go kind of back and then down again. So down, then that's the back. This is the C2, C3 bond that we're sighting down, and then we have that methyl group going down and back. And indeed, that's how we usually draw our molecules, as a zigzag, because that's the lowest energy conformation. So just last thing here, let's see here. No, it's my screen just shifted here, so let's see if I can move this over so you can see it all. Hopefully you can see that now. So you might wonder why we care about these conformations. And it turns out that when you're studying enzymes and how active sites work, or you're studying prion diseases or sodium channels, or why some molecules are more common in nature and some are less, why some reactions happen, it turns out that a lot of those things end up conformations end up contributing to the answer to them. So we'll see how conformation is important as we go on. And for now, you just want to add these ideas that molecules have different conformations, and some are more stable than others, and we're more likely to find the molecules in some conformations than the other. You want to add that to your picture of molecules.